in this case, we've been presented with a hydrocarbon, which the empirical formula we've been told is C₁₀H₃, and we've been told that the actual molecule has a molar mass of 492 grams per mole. So we've been tasked with figuring out, okay, well, what's the actual molecular formula of this particular hydrocarbon? Okay, so how are we going to work this out? Well, when I look at this, one of the things that comes to mind is, okay, well, what's the empirical formula? The empirical formula is the simplest, and some would say the smallest, whole number ratio or between the atoms of the elements present in the compound. Okay. The molecular formula, on the other hand, is the actual number of atoms of each element present in the compound, right? So represented as a formula, right? So we've been told the molar mass of the molecular formula in effect. We've been told the formula of the empirical formula. Okay, how do we get the molecular formula? Well, if I wanted to try and solve for this, one of the things I would try to do is try and compare the molar mass of the empirical formula and the molecular formula and figure out, well, if I'm scaling up the empirical formula molar mass to the molecular formula, what's the multiplier? That's the first thing I go for, trying to figure out what the multiplier is. But we don't have the molar mass of the empirical formula, and it's not given to us in the question. So I'm going to try and figure that out. How am I going to do that? Well, we've been told it's a hydrocarbon, it contains carbon, it contains hydrogen. So I'm going to use the periodic table. I'm going to work out the molar masses of the constituent elements. And you may already know what the molar masses of these constituent elements are, since carbon and hydrogen are quite common, right? So, but in any case, let's go through the process. So for carbon, which we have here, and we've got hydrogen here. So we can see that for hydrogen, we've got a relative atomic mass of 12, and hydrogen, we've got a relative atomic mass of 1, right? And for all intents and purposes, the molar mass is the same, right? So the molar mass, MR, of carbon is going to be 12, right? 12.0 grams per mole. And the molar mass for hydrogen, simply put, is also, it's going to be the relative atomic mass of hydrogen. So it's going to be 1.0 grams per mole. Okay, so I'm going to use these to try and work out the empirical formula of the compound we've been presented with, and we've been told it's C₁₀H₃. So I can use those, use that formula to create a calculation for the empirical formula. So in this case, as we would know, we would need to multiply the molar mass of carbon, so which is 12, multiply it by the number of times the carbon occurs in the empirical formula. So this is obviously denoted by the numerical coefficient here, which is in this case is 10 for carbon, and then we add this to similar for the hydrogen. So for hydrogen, we've got a molar mass of 1, so we do 1, multiply that by the number of hydrogens. In this case, again denoted by the numerical coefficient, which is 3, so 1 times 3. Okay, and so this would give us effectively an indication of the molar mass of the empirical formula. So you do that. If I invite you to have a go on your calculator to work out what you get when you try that out. Though I would say it's a straightforward calculation, you don't necessarily need a calculator, but anyway, in any case, you'd get 123, right? And therefore, based on that, we can say that the molar mass of our empirical formula, so this is C₁₀H₃, is equal to 123 grams per mole. Okay. Now, as I mentioned earlier, we do need to also work out a multiplier, right? And so the formula I'm going to rely on for working out the multiplier is that the multiplier is simply the molar mass of the molecular formula divided by the molar mass of the empirical formula. Okay, so it's the MR of the molecular formula divided by the MR of the empirical formula. Okay, and what's that going to give us? Well, that's in effect going to give us let's put the calculation together first before we go into what's going to be the outcome. So that's going to be 492, right? So that is the molecular formulas, the MR of the molecular formula, and this is the MR of our empirical formula that we calculated. So we need to do is equal to 492 divided by 123. And so if you have a go at working out what that is, have a look at what number you're going to get out of this, right? So if you do work that out, you should get that equals 4. Okay, so our multiplier is effectively 4x multiplier in this case. So the empirical formula, you multiply it by 4, you get effectively your molecular formula. So let's go through the process one element at a time. We're going to start off with carbon. We can see that the coefficient associated with carbon is 10, right? Hopefully you didn't well, if you saw that, we'll get to that anyway. But so for carbon, we're going to get 10, we're going to multiply that by 4, right? And that gives us 40, right? And the indication there is that we're going to have effectively C40, okay? And if we now move on to hydrogen, and we do more or less the same as we recall, for hydrogen, we've got a 3, okay? So the associated numerical coefficient for the hydrogen is a 3, so we're going to do 3 times 4, okay? And that's going to give us 12. And therefore, in association with the hydrogen, it's going to be H12, okay? And on that basis, we can effectively say that the formula for this particular molecule, the molecular formula, is going to be, if we consolidate this, it's going to be C40H12, okay? So this is going to be our molecular formula in this case. Now, one of the things I would like to bring your attention to is effectively a real life example of what C40H12 represents. So this is an example of one of the molecules that actually does have the formula, right, of C40H12. It is a lot of carbons, but it is also a real molecule. So this is effectively a planar 10-annuline derivative. It's not something you necessarily just come across as a common something that would commonly be found in a lab, but through experimentation this can actually be obtained. It's a planar molecule. Obviously we can see from the name, like it is a planar molecule. And just for clarity, this is like a generic name. It's not like the exact name of this particular molecule, but this is like a generic name for it, because anyway, so all three of these representations that you can see are actually the same molecule. So this is more or less the same as this. It's the same as this. It's just kind of different ways the same thing has been represented. For example, in this particular case up here, not all of the hydrogens are shown directly. The hydrogens are there, but the formula just doesn't show. It's kind of like if you're familiar with skeletal formulas, you've got part of it, not all of it, but part of it is kind of represented in a way where the hydrogens are assumed to be there based on the known valency of carbon, right? So you've got, like, you would have a hydrogen here, and it is shown anyway, shown in this diagram, right? So you have hydrogen, actually you would have a hydrogen here and here. But in any case, if you were to count these up, like the hydrogen showing, especially on this diagram here where they're quite clear, you find, if we quickly do that, 1 2 3 4 5 6 7 8 9 10 11 12. So you can see we've got 12 hydrogens. I'm not going to count up the carbons. You can feel free to do that in your own time, but yeah, this is actually a molecule which you can find a paper about this molecule. It's mentioned in the paper somewhere, but yeah. So but yeah, that's something you can explore. But yeah, in this case, as I said, the molecular formula is C₁₀H₃. Right?